Okay, here we are interested in what is the derivative of the inverse tangent of x. Okay, and you'll notice I have graphed here the function y equals tangent of x, shown in red. Okay, and do notice that we are graphing the tangent function over a restricted domain, over a domain where our angles don't get any bigger than pi over 2 and don't get any smaller than negative pi over 2. So let's indicate that. Okay, so we have that there. Of course, this is precisely the actual function that when we find its inverse, we get the inverse tangent function shown here in purple. So let's label that. Okay, now if we're after the derivative of the inverse tangent, then whatever this is should give me the slope of a tangent line to this purple curve at some given input x. So let's find a representative point to work with. Let's say the one right here, and we'll call the input there x. Of course, the height of this point is given by the y-coordinate, which is then just inverse tangent of x. So I can go over here on the y-axis and label that. Okay, and do remember that I want the slope of the tangent line at this point. That will be, at least when given in terms of x here, the derivative that I seek. Okay, so let's draw that tangent line in. Now, remember, this purple function and this red function under this restricted domain are inverses of one another. They do exhibit a really nice symmetry as a result. They are symmetric to each other with respect to this line here, this y equals x line, which we can dot in. Okay, like so. And so for every point here at x inverse tan x, there should be a mirror image point on the red curve where the ordered pair has been reversed. So in other words, the mirror image to this purple point is this point over here, whose x and y values are simply these x and y values reversed. So this is now at inverse tan of x, and the height here is just x. And just like this purple line is tangent to the purple curve at this point, there should be a mirror image of that over here going through this red point. Let's draw that in. There we go. Okay, and again, because of this symmetry, because we're just swapping the x's and the y's, notice we have a nice relationship between the slope of the purple line and the slope of the red line. A run over here turns into a rise over here. A rise over in the purple line turns into a run over here. So the role of rise and run has been reversed, which means the slope of this red line and the slope of this purple line should be reciprocals of one another, since slope is given by rise over run. Okay, so let's indicate the slope of the purple line with a purple M. Okay, so whenever we write purple M, we mean the slope of this purple tangent line, tangent at the point where the input is x. And in a similar way, let's write the slope of the red tangent line as a red M. Okay, so we have this as well. Now, going back to our original question, the derivative of the inverse tangent, that should give us the slope of the purple tangent line, which is purple M. So I'm going to write equals M. But this purple slope, we said, was the reciprocal of the red slope. So this in turn should equal 1 over the red M. Now, why do I rewrite this derivative in terms of a red M, the slope of this red tangent line? Well, I know something about the slopes of tangent lines to this red curve. This red curve, remember, is given by y equals tangent of x. And I know that the derivative of tangent of x is secant squared of x. And so if I want to find the slope of the tangent line to this curve, to y equals tangent x, at let's say pi over 7, that's just going to be secant squared of pi over 7. If I want to know what is the slope of the tangent line at negative 0.01, then that's going to be secant squared of negative 0.01. If I want to know the slope of the tangent line to this curve at this input value, then that's going to be secant squared of this input value. So I know what red m is. It is secant squared of this input value inverse tangent of x. Now, this isn't too bad, but we can actually go a step further. Keep in mind that the inverse tangent of x is an angle. Let's call that angle theta. And we know that if we take the tangent of this theta, we should get x out, okay? Which means we can draw a little reference triangle here for angle theta, say this one right here, where we force the tangent to come out to be x with a convenient choice of the lengths of the side. So I'm going to make this side x, this is the opposite side of course, and this the adjacent side 1, so that opposite over adjacent, or the tangent of theta, is x over 1, or x. Okay? Now, keep in mind, we do have to account for the possibility when x is a negative, and so our picture would change ever so slightly, but this picture here will certainly illustrate our point. Okay? So, without loss of generality, let's assume this x is positive. What is the secant squared of this angle theta? Well, of course, secant of theta is 1 over the cosine of theta, which means I need to be able to figure out what the cosine of theta is. Cosine is adjacent over hypotenuse. What's the hypotenuse? Couldn't we use the Pythagorean theorem here to find out? Isn't it required that this hypotenuse length is the square root of 1 plus x squared? But if that's the case, the cosine is 1 over this, and the secant of theta is hypotenuse over adjacent. The secant is just going to be this. So we have the following. Replacing the secant of theta with this radical, don't forget to square it, of course. But now, taking a square root and squaring it, don't I have this right here? Isn't that a nice expression? We have found the derivative of the inverse tangent of x. It is 1 over 1 plus x squared. That's it.